Alright, we're going to take the opportunity now to go over some of the homework questions that were assigned yesterday for Worksheet 4 in the Statistics unit. First question, the marks of a large number of students were sampled and the mean and standard deviation were 58% and 8% respectively. The data is normally distributed. So start here with the normal curve, and what we're going to do is fill in where our mean and the effect that the standard deviation would have. So the mean, we said yesterday, will be here in the middle, and the mean is 58%. And with a standard deviation of 8 marks, then the next will be 66. So if you went up one standard deviation, you get 66. Then you'd be 74 and 82. And going back one standard deviation, you'd have a mark of 50, mark of 42, and then finally have a mark of 34. So before we get into the questions, just make sure you understand what's happening here. So the mean mark on the test was 58. That means that half the students from here down had a mark less than 58, and half the students had a mark higher than 58. And the deviation from that you would expect was 8 marks. So from here the percentages, and these don't change when the data is normally distributed, and that's key in the question. You have to be told that data is normally distributed. Use the bell-shaped curve, or sometimes called the normal curve. So it means that 34% of students had a mark between 58 and 66, 13.5% had a mark between 64 and 74, 2.35 had a mark between 74 and 82, and 0.15% of students had a mark higher than 82. And then on the other side, the percentages stay the same. This is a symmetrical curve, which means that if you fold it here along this dotted line, it would fit over on top of itself. So in question A, for this test, students passed if they scored 50% or more. What percent of students passed the test? Well, you have to get 50 or more. So this is your benchmark, 50, and you count all the percentages from here up. Now you could add all these percentages, and that would lead you to the percentage of students that passed. Another way of doing it would be the curve represents 100% of all students. So if curve is all students, then we would just take away those that didn't pass. So you had, so subtract 13.5, 2.35, and 0.15. So what we're going to do here is add these percentages and subtract it from the total. And by doing that, you'd find that 84% of the students had a mark of 50 or higher. Question B, what percentage of students scored less than 34? So you find 34, and what percent of students were less than that? 0.15. If there are 60 students from our school who complete the test, how many will be expected to pass? So 60, and we're going to multiply that to the percent of students that we know passed. So we know that 84% of students passed. So to do the multiplication, change your percent into a decimal. So change percent to decimal, you divide it by 100, so 0.84. We would have 50.4, or since you can have 0.4 of a student, 50 students pass. Okay, let's say across the province 2,500 students wrote the test. How many scored 82% or more? Well, let's find a percent that got 82% or more first. And that's here. And that's 0.15%. So 2,500. And we're going to multiply that to 0 decimal. Now, check up here. This percent needs to get changed to a decimal. Put another 0 in there. So again, you take the decimal 1.5 divided by 100. So you have 2,500. .75 students, approximately 4 students will be expected to get a mark higher than 82. Next, you have 2,500 students wrote the test. How many scored at least a 42? So scroll back up. So you had to get at least a 42. So we're not interested in those who got less, just everyone from here up. Again, you could count all the percentages, 13.5, 34, 34, 13.5, add all those percentages. Or it might be faster just to take away the percentage of students who didn't. So there's 2 ways to do this. First, let's consider all those who got marks higher than 42. So we would add the percentages. So we take 13.5, we add 34, 34, 13.5, 2.35, and 0.15. So 97.5% of students got a mark 42 or higher. Change the percentage to decimal. So 2,437.5 students, or 2,437 students, had a mark of at least 42 on the test. Another way to look at this is consider those that didn't get at least that mark. So if you add 0.15 and 2.35, that's 2.5% of students didn't get a mark of at least 42. So 2,500 times 2.5%. Remember to change that percent to a decimal. Decimal there. That would be the right place to have it. Just fix that. There. So here we'd have 62.5% of students didn't get a mark of at least 42. So if they didn't, and whoops, one second. Alright, just clean that up a little there. So 62.5 students didn't get a mark of at least 42. Take that away from your total, and we still come back with the same answer. So you don't need to do both ways, just whichever one you find works for you, use that one. Okay, the next question I do is number 2. It says the mean mean June midday temperature in one time is 36 degrees with a standard deviation of 3 degrees. Assuming the data is normally distributed. Again, that's the key part here. Is that if you're told that the data isn't normally distributed, then you wouldn't be able to use a normal curve. And let me just fix my pens. So what percent of days had a mean temperature less than 30? What percent of days had a temperature 33 degrees or more? And the town issues heat advisory if temperatures above 42 degrees. How many days were June required to have a heat advisory? So you don't need to draw the normal curve every time. What you can do, just draw your percentages in. So here, let's think of it this way. So I won't draw the top part of the curve, just that your mean will be here. And we know that the mean temperature is 36, standard deviation of 3. So 36, one standard deviation above is 39, one standard deviation below is 33. And then you have 42, and then your second standard deviation, so this is one standard deviation above, 2 standard deviations, 3 standard deviations. And one below, use the minus sign to represent one below. This one below the deviation or the mean. That's 3 standard deviations below. So I'm just not drawing the top part of the curve. And your percentages were 34, 34, here 13.5, 2.35, and 0.15. And same on the other side. And you'll get to know these the more you do the questions. So what percentage of days had temperature less than 30 degrees? So less than 30 means we're going to look at 30 and go below that. So what percentages are within these from 30 below? So you've got 34, 13.5, 2.35, and 0.15. So from 30 below, there's 2.35 and 0.15. So percent of days that are less than 30 will be those percentages here. So you'd have 2.5% of days. So what we're doing, we're looking at where a benchmark is, and then percentages for each of those categories. And remember, they come from here. So we'd have 2.35 and 0.15 in our case. What percent of days had temperature of 33 degrees or more? Well, 33 degrees or more will be here. So we're adding 34. Now, we know that the mean is 36. And on, let me get a highlighter. So from our mean up, we have 50% of our data. So remember what you said there at the beginning of the class, that from your mean up, you have 50% of your data. So it's not necessary to count all the percentages if you can understand the curve. So 33 is one deviation below. So you have 34 degrees. And then from the mean and higher, you have 50%. So you have 84% of your days. And the town issues a heat advisory if the temperature is above 42. How many days in June was their heat advisory issued? We'll get the percentage first. So we're looking for 42. 42, so we're one deviation, 2. So 42, we are looking at the percentages of 2.35 and 0.15. So 2.5% of the days. But what number of days? Well, you need to know how many days are in June. There's 30 days in June. So we'll multiply that to our decimal, change the percentage to decimal, and quickly checking with a calculator. Alright, so 0.75 days. So what this means, you can't have 0.75 a day. In other words, it would be extremely rare to have a day of 42 degrees or more. Not saying it wouldn't happen, but the likelihood of it happening is extremely small. Okay, your next question is number 4. It says the mean July rainfall in Waterville is 10 millimeters with a standard deviation of 1.5. Assuming this data is normally distributed, and then we answer each of the following questions. So first thing to do is draw a normal curve for yourself. So I'm going to pause here. Alright, so instead of drawing out the entire normal curve, again, just draw the bottom portion. Your mean is in the middle, so that will be 10 millimeters, and there's a standard deviation of 1.5. So one standard deviation above, 11.5, 13, and then 14.5. And then one deviation below, 8.5, 7, and 5.5. Your percentages, 34, 13.5, 2.35, and 0.15. Same on the other side. Okay, so what percentage of days in July had a rainfall of at least 13 mils? So you have 13, at least means 13 or more. Well, 13 is your benchmark, that's your starting point. So you go from here above and add your percentages in your distribution. So 2.35 added to 0.15, you have 2.5% of days. How many days in July would you expect to have rainfall less than 5.5 mils of rain? Well, first get the percentage. So less than 5.5. Well, that's 0.15%. So change that to a decimal. And then you need to know the number of days in July. Well, there are 31 days in July. times 0.0015, and that will give you an answer of 0.0465. So extremely rare for July to have less than 5.5 mils of rain. How many days in July would you expect to have more than 7 mils of rain? Okay, so how many days in July have more than 7 mils? So we don't care how much more, just more than 7. So again, you can look at this two ways. You could look at number of days in July that have less than 7. Figure out the number of days in July that have less than 7 and subtract that from 31. Or find the percent of days that have more. Well, if I want to consider the number of days that have more, remember the whole chart represents 100%. If you add up all the percentages, you would get 100. So 100 includes every single day within July, 100% of all days. Subtract from that the days that have less than 7 mils. So that's 2.5%. So we would have 97.5% of days in July that have more than 7 mils of rain. You can also get 97.5 by adding all the percentages and just highlighting the yellow. So there are 31 days in July. Change your percent to a decimal. And then 31 times 0.97. And you would have 30.225, or we would say 30 days. Factory produces packages of chocolate chips. One product is semi-sweet milk chocolate chips, which are sold in packages of 250 grams. During yesterday's production run, 80,000 packages were produced. A large number of them were tested and were used to determine that the mean mass was 242 grams with a standard deviation of 4 grams. So start by doing the distribution. And yes, we're going to assume it was normally distributed. Someone is waiting for to pick that up. That didn't say that, so I'm going to say it here. So you have your mean, and that is 242 grams. So your mean helps to summarize your information too. Instead of having always look back to the question. So I usually do that over here. So one standard deviation above, while writing out 4 each time. So 246, deviation above, 250, 2 deviations, 3 deviations, 254. And same works on the other side, just that this time we take away 4 grams. So 238, 234, and 230. And just check our numbers. Percentages. 13 and a half, 2.35, and 0.5, 34, 13 and a half, 2.35, and 0.5. How many packages do we expect to be underweight? Well, first are 80,000 packages. Now, when we consider underweight, companies labeling them as 250 grams. Anything less than 250 grams, they're considered underweight. So 250 is here. So you could add all these percentages here, and you will come up with 97.5. Or you could look at it as here and count the percentages above. Switch back to the pen. So if we look at above, adding your 2.35 and your 0.15, 2.5% are at the weight or higher. So since our chart takes in 100%, if you look left to right, take away the percentages of those candies or packages that are at the correct weight, we'll be left with 97.5% are underweight. So how many packages would that be? 0.975. So 80,000. So 0.975. So that would be a problem. 78,000 of your 80,000 packages are underweight. However, a company would allow for not being perfect, and probably wouldn't reach 242 grams, probably would meet the minimum to reject it. So the company has decided that if it's less than 238 grams, they're going to reject it. How many packages we expect to be rejected? So we look at 238 here. So what percent of packages are less than that? Well, we have a 13.5 plus 2.35 plus 0.15. So we're adding these three percentages. So if we add those, we get 16%. 13.5 plus 16%. So 16% are to be rejected. Now to get the number out of that production run, change your percent to a decimal. Multiply by 80,000, that's the number of packages that were produced that day. And we get 12,800 packages. Reject it. Alright, last question. The company makes parts for a machine, the length of parts must be within certain limits or they will be rejected. So if the parts are too long, they're down, too short, cancel those two. The number of parts are measured, and the mean and standard deviation calculated is 3.1 meters and 0.005 meters, or 5 millimeters. Assuming the data is normally distributed and 99.7% of parts were accepted, what are the tolerance limits? Well, okay, so we didn't talk anything about tolerance limits, so What's this 99.7%? Well, what we're asking is what limits, how short can the part be, how long can it be before it's rejected? And you might not have an idea how to start, but really you do. So start with considering a normal curve. And again, we're not going to draw on the top curve part here. It just gets messy. So we have our mean. So the part can be 3.1 meters long. And we expect a variance, if you want to think of it that way, or standard deviation, 0.005 meters. Now we didn't say millimeters. You want to keep everything in the same units there, but that is 5 millimeters. So we need 3.1 and 1 standard deviation above, 2 standard deviations, 3, and we have 1 below, 2 below, and 3 deviations below. So let's think about our lengths that go in here. And I'll just put our lengths here, 3.1, 3.105. So add on your deviation. Now we're going to go below, so what you need to do here is subtract it. So 3.095. If you figure, sometimes decimals and subtraction, people get a little mixed up there. Think of 3.1 as, think that 1 is like 100. Okay, the zeros can keep going on forever. So 100 take away 5, go through 95. 95 take away 5, 90, 90 take away 5, 85. Now where are they getting the 99.7%? Well, let's think about your percentages that go in here. And percentages are 34, both see 34, 13 and a half, each side, 2.25, 2.35, and you get 0.15 and 0.15. Now, something to remember is that all the percentages add up to 100. So almost all the parts were accepted here. How many weren't accepted? What percentage? 100. Take away 99.7. So take $100, take away $99.70. We left with 30. How are we going to get 0.3 out of this? How did they figure that out? Well, if you look here, 0.15 and 0.15. These are the areas that get rejected. So if it's any more than 3 deviations below, it's rejected. Any more than 3 deviations above. If you add 0.15 and 0.15, you get your 30. That's the limits. So the limits on the part are here. So the part can be 3.085 meters, or 3 meters and 8.5 centimeters, or could be 3 meters, 3.115 meters. So that's the tolerance in your parts. It's allowed to be this short, that long. Happy place is 3.1 meters. So think of it this way. Your part is well let it go to be a little bit longer, or they'll even accept the part if it's a little bit shorter. Alright, that's it.